Hello everybody, welcome to another stream. And the camera's in the wrong place. Kabam. Boom. Right, so last stream we were working on adding support for block compressed texture format, so BC1345 inside the GPU module. So inside the Vulkan abstraction basically. And so now we have our block compressed texture, there we go. We can kind of see it a little bit underneath, and that is because that's the normal map. That's the reason why you're seeing the actual texture underneath, but then you're seeing this really blocky looking texture on top, and that is obviously all the other channels, the albedo, emissive, and everything else. Because the normal map is not block compressed. So, now what I would like to do is just quickly double check the stuff we did last stream, because I've been thinking, and perhaps maybe I got some of it wrong. So I want to just quickly start there by creating a new texture and just following it through in the debugger and just double checking some things to do with like the sizes and stuff. Call it test. We'll be testing BC1. Create a static texture. And then after we've tested stuff from last stream, what we're going to get on to doing is porting over this open source block compressor on the GPU from, believe it or not, the people over at Xbox have open sourced this. So it's like 600 lines, it block compresses BC1345 inside the shader, and supposedly does a reasonably good job. Hopefully it's good enough for us. If not, we might rely on some third-party tool to do it on the CPU side. Or there is a more complicated shader we could port as well. They've got multiple of these. They've got a higher quality one, by the looks of it. In some other repo I've seen it. This is fast block compress. They've got another one, I think. I can't really see it here, but yeah. Maybe. I've seen in another repo from Microsoft. Can't really see it here though. Cool. So let's just quickly test this out. So I want to have, let's do 4K. Like a 4K squared texture. Not 4K, yeah. It's confusing now. Not UHD, I think it's called. But anyway. Mid levels 1 array layers 1. So what we'll do is we'll put a breakpoint here. And then we'll open that right up in the debugger and have a look. All right. So step into here. Now there's a call to the back end. It's here. So yeah, we ended up doing this sort of divide, and I'm not sure if this is correct, because when we didn't have this, we were over allocating so much memory. So I just want to get a feeling. Well, not get a feeling, just actually check the. So it's dividing it by the block dims. So it's dividing it by 4 on each axis, basically. That's what block dims end up being. Because if I didn't do this, when I asked Vulkan how much memory I need to allocate for this image, it gave me a big result, but maybe that was because of the number of MIP levels we had. But it seems to be bigger than if we had it uncompressed. It was very strange. So I just want to double check all of this. So we create our image, then we maybe create another one to alias the same memory basically. And then we get the memory requirements. So now the memory requirements, let's see how big that is. Probably better if I just printed it out into the terminal anyway. Right, so so for 4K texture, that's only 524288 bytes, which is like that's 512K basically, isn't it? Right. It's a bit small. For BC1, for 4K, yeah, so it seems like we don't need to do this division here. Let's go into the Vulkan. Create image. Yeah, so let's go ahead and just print out. So I could say resource name, size, something like that, yeah. And yeah, you can also do it again. So it'd be resource debug name, this, and a size and alignment. So we print those out. We should be able to see that before it exits. Yeah, so it's called test, and then it prints them out there, right? So, right, but that's not the number that we had before. That's a much bigger number. So I'm wondering, so that's because we max it here with this one, with our alias. So we basically have, so because we, right. So this could be where the bug is. That might be it then. Right, so because we need to be able to write to it from a compute shader, so that's known as a storage image. Right, we've got a sample image, and that's when you just want to read from it. Or you want to only sample from it. But if you want to sort of read and write to the individual blocks, there's a thing called a raw variant, and we have that for sRGB as well. There's a raw variant because you can't access the sRGB one in the compute shader. So essentially the storage image can have a different format for certain GPU image formats. So we've got BC1, we can alias the memory and do the 3232 UINT. Now, the problem is with what's going on here by the looks of it is ends up being a bigger size or something. So let's go back to here, let's move this print, well not move, let's copy it up to before we do the raw variant. So the raw variant, we create two images without any memory. We get the memory requirements, take the maximum of all the memory requirements, and then allocate one block of memory, then bind the same memory to both of the images. And that will allow us to alias the same block. But I'm thinking we're getting two different results back. Yeah, see, one of them is small, the other one's big. So this is what was causing us a problem. I don't know why it's so big. The align is the same. Okay, so let's go. So let's undo that thing then. Oh, well, no, we'll do it in a bit. Let's try and get the numbers the same. So if we go to a BC1 texture format, that is, from my understanding, 64 bits per... Oh, it's per block, isn't it? Right. So I can't alias it, I can't alias it like this. This is where the problem's been coming from. Yeah. Right, I get what's going on. Okay. So this isn't in... Right, I got it now. I got it. So when we create the image, with create image info, it doesn't want it to be in blocks. It does want it to be in pixels, because I did think it was weird being in blocks. But when we create the alias for it, we do want to change the extent such that it is in blocks. And that's the reason why it's coming out so much bigger. Right, that makes a lot of sense. So it is in pixels. So this one will be in BC1, right? But then we have a sort of a different image which is aliased in the same memory. And that will be in the format 3232 events. That's two U32s together making a U64. And we divide that by the number of pixels in a block. And that will get you... Yeah. Right, that makes a lot of sense. Yeah. So that will get us the correct... So where's those block dims? Yeah, so that means now when we do these, they should both report the same size. So the first one, there you go, they both report the exact same size here and the same alignment. Amazing. Cool, that's better. Now, so the question is then, when we go back, if we go back to graphics and then change it to BA, so it's a 4K squared texture, let's make it be 888 sRGB. Right, let's see what we get there. So that this is, what is that? It's 8 megabytes, isn't it? It's about 8 meg for a 4K in BC1. So this should be 64. Yeah, there you go. So that's 64 meg. It's a lot of savings. Amazing. Well, BC1 is only RGB, and obviously it's block compressed to 4x4 tile. And then 888 is obviously 1 byte per pixel, and it's RGBA. Okay. It's pretty good then. So I'm glad we fixed that. So one more thing I want to double check in this backend before we port the code over is there any more places where I'm using this sort of block dims, which I divided by or divided by it. So texture copy wants it to be in blocks, I think. I'm pretty sure. Yeah. We'll soon find out, I think. Yeah. Right, let's just quickly double check it. So it was like buffer to image copy, wasn't it? That one. Image extent. Right, copy regions for the image must be aligned to a multiple of the text or block. Yeah, okay, so there's no division by block dims. So I've got that assertion up above. Amazing. Oh, what about texture copy though? That's different. Crap. Copy image. Hey, Cranston. What does the texture copy do if your 8 is in the same memory? Is it just equivalent to a cast? Yeah, so they're two completely different images, but they point to the same memory. So it seems to be working for now, but basically, I think yeah, there's some stuff to do with barriers, which is a bit tricky to get right. I think I've got it right. But yeah, it's a bit like casting a pointer, basically. It should be fine. The thing is about the pipeline barriers is you need to make sure the caches are flushed. And it's in the right image layout as well. And I think I get that stuff right. So that's the only thing you gotta get right is the pipeline barriers and stuff like that. You should usually use image views and that helps because you sync with the image, but I've done it with an alias on the actual image memory. Yeah, maybe I could get away with that doing a full image. What was my problem with... I'll look at that in just a second. Because if you can just change... Oh yeah, that was it. I think I wanted to tell it the formats up front. It was something like that. But no, I'll have a look. Must be a multiple of block extent width. There you go. Okay, so it's not in. Right, this makes a lot of sense. I was thinking, I was just reading the documentation wrong. Right, it's just not any longer this divide thing. Alright, nearly there. Yeah, I'm not doing bad, Cranston. How are you doing? I'm doing okay, thank you. I finished up on my task at work today, which is really cool. Got all everything done. I just gotta obviously get it in review and get it all checked into the main code base now. which is another whole thing. But things going good. The little man's doing well, he's walking. So I'm having a lot of fun with him at the moment. Right, so this aliasing thing. Oh yeah, the reason why I had to do a whole separate image is because the usage flags had to change. I didn't want it to... Yeah, I couldn't have it as usage storage or something like that with an sRGB texture format. It was bloody dumb. So annoying. So let's create another whole image. Yeah, it's good fun. He's grown up now. Is at the right age where he could really do with a... Well, we could probably handle a lot better when there's another... If he has a sibling now, basically, because he's walking. Let's hold it. Let's holding him now. Rightio. So I think that's all of our issues sorted out. Just run it again now, and we should just see this terrible block compressed texture, which is obviously just invalid data. No, because I hit a trap. Uh-oh. Right, what is this for? The copy image exceeds resource width of 32. What is going on? Great. Oh, it's probably using the storage image, isn't it? That's got the divide by 4. Maybe. Let's have a look at that. So where's that? GPU Vulkan. So the image, yeah, I'm using the storage image here, right? Which is problematic because the storage image on a block compressed texture is divided by the number of, or how many pixels in a block. So it's divided by 4 on each dimension. And the sample image is kind of the full resolution. There we go. So just look around for all those. Upload needs to do it as well. And read back. Right, I think we're good. Damn it. Right, now we're off by a half. For some reason. We're off by a half. Material cache load material. What is the short of block compression? Lexical like LZ. No, it's more like So we go to BC compression, which stands for block compression. So BC is the block compressed format for PC. Excuse me. So this is a good article to read on it, but the TLDR is basically, so the word block should really be called tile, because it's like you would use it for two-dimensional things. Blocks are typically what you would refer to as a three-dimensional thing, but so the naming's a bit off. But BC is it block compresses 4x4 blocks, a bit like JPEG in a way, in a sense. It's lossless compression, whereas JPEG's got a different form of compression. It's like a, yeah, if you look into JPEG, it's actually quite smart, and it's quite fascinating actually. But it's like JPEG in the sense of it's a lossless compression, but it's kind of different though, under the hood. So it works on like 4x4 blocks and it essentially compresses it down into to 64 bits, for instance, for a BC1 texture does that. So this would be a 4x4, which is 16 bytes typically, and it will compress that down into 4 bytes. So it's quite good compression, but you obviously have artifacts from lossless compression. And it all depends on how good your encoder is as well. So there is multiple BC formats. There's BC1, which is like the original, which is good for RGB data. BC4 is for alpha data, basically, just single channel data. And then BC5 is two BC4 stuck together. BC3 is like a BC1 and a BC4 on the end. And then BC2 is something different. People don't really use BC2 apparently. But yeah, BC6 and 7, the latest ones, these are a lot more complicated. We will not be using those. One key thing is they're very local to facilitate efficient parallel reads on GPU, yep. Yeah, it's pretty good, isn't it? Pretty great compression ratio. But yeah, you obviously, things won't look exactly as good, but the amount of, on the GPU you have hardware decompression as well. So you just sample it with the standard texture sample API, and it does all the decompression under the hood on that block. And if you got some neighboring, and typically, like as Cranston was saying, is very local. You have neighboring pixels within the same wave at the same time fetching the pixels next door. So when you decompress a block, it's sharing it across all those other samples and everything. It probably does it in a across the compute for the whole compute unit. Maybe, I don't know exactly how it works, but so you got that savings as well in terms of using the hardware, but you're also saving like your caches. You're populating like more of your pixel data fits into less cache, sorry, into less memory, therefore more of it fits into cache, and therefore there's less main memory to cache reads as well. So it's all pretty useful stuff. Helps speed up everything. So here we've got some, it says that we've got an extent of 128 bytes, but there's only 64 width on the sub-resource for some reason. I don't know. Maybe I'm off by one on the MIP. But this wasn't here before, so I'm a little bit confused. So on the albedo when it's the first one. Yeah. So I guess I can put a breakpoint right in here, just fire it off, and we can just see, you know, if it's the first one that causes it, amazing, we can just dig right in there and give it a little bit of an analysis, really, about what's going on. So, there we go. So if we hop into the, yeah, okay, so it fails on the first one. Amazing. So on this texture copy right about here, we do a couple of syncs, we get the destination and source, so let's look at the destination texture structure. Well, we see here that it has got dimensions of 128 squared. So what's happening is we must be initializing the texture with an invalid. Wait, oh, it depends what MIP we're accessing as well. We'll look at that. So the source image, what's that? That's a 4K. Okay, so it's the destination we're obviously going out of bounds on. That's what it was saying, right? Yeah. But it's saying source offset plus extent of 128. Don't know what's going on. Just take a look at some of this stuff here before it sends it down into the other layer. So let's do copy dims is 128. 128. We're just making sure here that it is multiples of the blocks. We do our copies, which seems to make a lot of sense. Right, so we hop down into here. Yeah, what is the MIP level? Source MIP 5, what's destination MIP? Ah, my source MIP might be wrong. Ah, crap, I deleted that shift right. Ah. Right. So in my texture copy Vulkan code, I actually deleted the shift right by MIP. And then I do need to put a max there. That's what I needed. Alright, let's bring it back. Whoops. So yeah, we take the dims, we shift it right by the MIP, then max it with 1. And that will be what we need for the extent when we do the copy. Right, okay, I gotta delete the breakpoint. Okay, so now we should see a very terrible looking sphere, which is very blocky. There we go. So we're seeing more high resolution blocks now, because our resolution was wrong. Now we're seeing the texture in there because that's the normal map, and we're not block compressing the normal map just yet, because I don't think we could be able to block compress the normal maps and still get good looking normals. But it might just be because my normal map is a little bit wrong. I don't know. So let's take a look at some of this in the texture viewer. So called block compressed albedo. So yeah, we're seeing it here, it's just very blocky, isn't it? Because we're basically copying regular pixel data to a block compressed format, I think. Something like that. So it's not going to do a good job. Now this is where we need to do the actual block compression manually. Right, there is a problem. There is another problem as well. What was it? Oh yeah, one more thing I wanted to do before we get in supporting that shaded code to do the block compression on the GPU from a uncompressed image. I want to make sure that we add just a few more formats. Should be very quick. I think BC1 has a couple of other variants which might be useful. There's some signed norm variants. I might put those in. Hey, Dyson Slice, welcome. Hey, question for you. Is there a way to temporarily hide all the comment messages? Hide all the comments? What do you mean in the code on... Well, what do you mean in your text editor? Your text editor could support that feature. I don't know, it's a text editor feature, right? Maybe. It's just, what text editor are you using? All right, let's go to Vulkan. That one. There is BC1 new norm. Right, there's BC4 signed norm. This could be useful, and BC5 signed norm. So let me just add those two. We're not doing BC6 just yet. We might do them though at some point. So BC4 norm. I think these might be useful. Let's get them in. So let's hunt for all of these ones basically, and we'll get in there and... Yeah, I think I'll snorm mode. Yeah, you wouldn't want to delete the comments though, because you can accidentally save it or whatever, and you could put new ones in there, and the editor could crash. Yeah, it all depends on what editor you're using, right? The editor supports, yeah, folding sometimes, so you can fold comments away. That's the thing. But here's the thing, Slice and Dice. If you're writing a lot of comments on every single line of code, you're probably not writing readable code. So the thing is comments are only useful when they describe something which is not obvious by looking at the code or just looking into a function it's calling or whatever, right? And reading what that does. Like if you, I see a lot of people write code like this, right? They'll be like, I see this so much, and it's just kind of silly. People are like, they think they're being helpful. They're like, initializes the backend, the GPU backend. Yeah, and they'll do this for like every single line of code, and it's like, obviously, right, I've named it GPU backend in it, right? That tells you what it does. That comment is useful, so useless. So just be careful, like only put comments when a block of code isn't sort of apparently obvious when you're just sort of reading over it. But this could probably be refactored into being a function call for initializing intrinsic resources, maybe. But yeah, rarely put comments in, because the more comments you have, the more stuff you have to filter through, basically. Yeah, well, it's relatively neat. It can get quite wide and messy sometimes, though. I try and take passes to clean my code up when I go and add new features and areas. Right, I think we're in a good place now. So, thankfully Microsoft, right, I didn't think I'd ever be saying this. Oh, wait a minute. Let me hold off on my praise for Microsoft. Don't think I'm quite finished yet. Hang on a minute. I gotta do the Vulkan one as well. Nearly there. Yeah, then GPU Vulkan. Use the Snorm ones. I don't know if this would be that. It might just do the ×2 take 1 for free. But maybe the format's a bit different, we'll see. Okay. Yeah, now out of date novel, that's a good way of putting it. Yeah. That is very much how comments do become. Because comments are sort of grayed out. And then when you come and edit the code, which is very, it attracts your eyes, you're gonna edit the code and then forget to edit the comments. It's another one or two. Very common. Right, so thankfully Microsoft, right, I never think I ever say this in my life, but they done something good where they've open sourced a block compressor in HLSL. So we're going to take this, we're going to port it over. Now I'm pretty sure this is under the MIT license, so I am going to be thanking Microsoft as, there we go. Whew, I can use it. So attribution. I didn't think I'd be saying this, but I'll be thanking Microsoft whenever this game gets released. Microsoft, what was it? The Xbox AGT samples for the fast block compressor. But it depends if we use it, right? But I'll put it there anyway. There we go. So, what we're going to do is go to the graphics shaders side of thing. And we're going to find a place just to throw it in the shader code, a bunch of utility functions to basically block compress color data, grayscale data, that sort of thing. Be pretty lit. So we should be able to just stick it as utility functions. I don't know. Draw, probably after draw might be alright. I don't think I ever want to draw with it, to be honest, but draw should go quite high up. I'll put it above materials. So block compress. Now Microsoft has actually some other open source code under MIT license. I think it's part of the direct text which is short for direct texture, right? TEX. So there's an even more complicated set of shaders. I think there are like 1,500 for each block compressed format. So they're quite complicated, and they have like all sorts in there. These ones look very simple, and there's 4 of them in like 600 lines of code. So we'll see how good quality these are. And if we need something better quality in the future, we can just port the other ones over, or we could use a CPU side thing. We'll see. So yeah, let's just copy it all in. Static sampler SO, MIP point, clamp, right, we'll keep an eye out on that one. So here we go. Yeah, mate. Right, so unfortunately it's got damn spaces. Right, like a Python developer or something, eh? Spaces everywhere. But anyway. Right, compress 1 MIP thread group width. It's not even used anywhere. So I get, is that used in the actual block compress shaders? Hang on a minute. So BC1, compress 2 MIPs, tail MIPs. Right, so there might be compress 1 MIP thread group. There's a way to compress 2 MIPs. Let's MIP 0 out. Oh, then there's a tail MIPS for all the other ones. Interesting. Right, is that a special downsample? Ah. Interesting, we'll keep an eye on that one. Is there a retab in Helix? I'm in Helix, remember? No. Yeah. It's not going to do it. Alright, so BC1 tail MIPS. 16, 8, 4x4, and 1x1. What's it talking about? Is it fixed to a certain res? Alright, let's just get on with the porting. We'll worry about these in a bit. So, blocks per row. Right, we'll delete these, we'll look at them later. So this is a block compress constant buffer. I can't see this anywhere else, so we're going to get rid of that. What is this warning? What is this warning saying? So sum of temporary registers in indexable temp registers times 256 threads exceeds the maximum total of 16k. Performance may be reduced. I don't understand what it's saying. When it says registers, you think like VGPRs and SGPRs, but That's per wave anyway. I think this is just an old thing. Packs of 3 come into you and no crap. Right, so here we're gonna call it like pack. See, 565. So that packs into a yeah, we'll just do that, I guess. Where'd the music go? So we're gonna round, and then we're gonna cast that to a int, and then we need to multiply. And there we go, so RGB, then shifting, packing, done. So it packs into a 16-bit int basically. But we have C32 because we don't have 16-bit ints. So texels to UV. Convert a texel to UV coordinates used in a gather call. Oh, so that 1 over texture width was actually in, but it was called G1 of the texture width. Yeah, I don't know how their code compiled. It's there. Oh, they've passed it in. Right, okay, so. Yes, this is specifically for doing square textures. Luckily, we're doing square textures. This seems, yeah, limited to square. How often is this thing used? Only in 2 places. Alright. We gather from the bottom right corner of the texel. Yeah, so it puts it in the middle of 4 texels, basically. That's why I added 1. So it's a kind of a specialized gather. I might just inline it manually. Not really interested in the function. Right. Round 1.5 can evaluate to 1 and... Oh, can it? That's very true, isn't it? I forgot about that. Yeah, so typically rather than a round, you just will let it truncate, but you add 0.5 instead. That's a good point. Floating point, eh? best and the worst format. Yeah, that makes sense. So, yeah, add. It's better. Thank you. Right, so where's the text source? That's the input text source. So you make that into a variable. Yeah, that'd be better. And then we just simply, what is that? Dispatch within, all right. So I've got a, cast. Right, so that'd be a UV. And voila. Cool. So load text as RGB, load the 16 RGB texels that form a block. Right, then it puts them out. So I don't really have an out parameters. I was thinking actually I could probably get these things to work in the compiler, but yeah, then I have to go back and do compiler development. I was thinking maybe I could make pointers work. I just have to be very careful about. They have to be always pointing to function variables or something like this. But until then, so we'll call this a BC block or block texels. Okay. So float 3. There we go. So we'll just return the whole structure. It's not a big deal on shaders. It all gets inlined, so it doesn't matter. Right, so in terms of the inputs, we need some form of texture. So in our case, that'd be a HCC texture something or other. So this, yeah, we've got to be careful. Is this, how often is this? Oh, it's RGB, right? So that would be a text, oh, it's a sample texture 2D, one of those. Yeah, texture. Like, I don't know what sampler you'd want. You probably just want a standard clamp one. Anyway, we'll remember they use a global and get that, to be honest. What sampler did they pass in? Where's load texels? Right, so it loads the texels with G sample. And it's just passed in. Right, I'm just gonna imagine it's just gonna be a clamp one with a linear sample maybe. But it's using gather anyway. Very nice. So inverse texture width. Thread ID within dispatch. What do we call that in our code base? We call that a thread index, isn't it? Local index. Dispatch local index. Cool. Hey Sam Kolak. Thank you so much. 29. Oh no, it's not there anymore. I don't know what happened. Thank you though. Think of it. All 23 24-bit integers can be precisely expressed in float. And we seem to be dealing with floats representing at most 6-bit integers. We should be safe. Maybe. Still, you won't be able to exactly represent all of the integers. So it might go below or above, right? Yeah, we don't know. Alright, so let's carry on with the conversion. We gather from the bottom right corner. Text, all that'll do. So that's the reason why there's a +1. So the problem is mine is top, kind of bottom left origin, or is this top left origin? But if I do that still, then it's gathering from. You know what? Let's just delete the comment. Let's delete the comment. Use brain, figure out what's going on. Much better. Right. So that's looking all right. So now we've just got to get this sort of sampler right. What sampler are we using? So I think for the sampler, I think I call it HCC RO sampler. So I think we can look in the globals basically, and there'll be a clamp linear sampler that we can just grab, and that ought to be good enough. So I don't have to pass that in or anything like that. So every time we see samp, we just say sampler now. Fix all that up. Interesting, there's quite a few of these. Yeah, it's got a full-on downsampler thing going on. It's interesting. Very interesting. I wonder if we can... We probably won't be able to use the custom AMD downsampler, then we'll probably have to use this code, which is understandable. Maybe. I wonder if we want to use this downsampler or use AMD's downsampler and then block compress that result. I wonder what will be better. Because it seems like this block compresses MIP 0 and then also has code to take the MIP 0 block and then downsample that. So I wonder if it might just be better just to block compress an already downsampled image. It might come out better quality, maybe, we'll see. Because we already do that. And it's pretty quick anyway. I'm quite happy with the downsampler we've got. Right, so it's load text source RGB. So we've got this sort of like red. So that's just something like this. Now, this gather thing. So it'd be something like... Oh. So in HCC we've got a thing called sample. I think it's just called gather actually. Gather sort of this red, green, blue thing. And then texture 2D, one of them. So it's the texture that goes in, then the sampler. Might just call it texture to be honest. Sampler, then the coordinate. Now these are gathering from like, why are they gathering from? Oh, that's the offset, isn't it, that they're doing? Yeah, we didn't have that. Crap, but they've got this offset thing. What is that doing? Right. They have that support in HLSL. So they're offsetting. Yeah, they're doing a very smart fetch of 16 pixels, basically. So this does a 2x2. And that does a 2x2 to the right, that does a 2x2 down, there's a 2x2 down and to the right. So yeah, that's all it's doing. So, yeah. Right. I might have to change how this code works as well because my textures are addressable from the... Actually, they're not addressable from the bottom left. No, I flip all my textures upside down, I think. Something like that. No, it might be okay. Yeah, it should be fine. So we've got to change this though. So this is Z. Just go around and replace all those. I don't have array literals on my... Do I? No, it'd be W, wouldn't it? Hang on a minute. Why is W encoded into... Oh, sorry, yeah, it's 4 pixels in it. So yeah, it's the 4th red pixel. Alright. Yeah, okay, easy. Okay. Alright, didn't work out too well. Alright, next one. So that is Z. Then this be the X. I'm interested to see like how the block compression thing works. I think they take two colors and put that into, they put two colors in from different edges of the block or something like that from skimming how it works. But there might be better ways to block compress it or not. We'll see where that is. So Y. Okay, that's looking good. So the next thing we need to sort out is like these neighboring ones. Now, how are we going to do this? So what we need to do is get some sort of like offset in UV space. So we already have inverse texture width. So that's 1 divided by the texture width. So that's how big is 1 pixel in UV space. That's all it is, right? So we can get that right just by doing 2 times, right? And this will be what's known as that sort of UV just call it offset. It's a 2 pixel offset basically. So all we're saying is so I might change we'll make another one called offset UV. And that'll just be equal to UV in this case. So offset UV. Now we copy these, place them here. Then obviously remove the declaration part. Then we simply just change offset UV to whatever we need it to be. So that would in this case be add, and then put in a vector. So in this case, we just want it to be offset along the X and then 0 across the Y. And then we do the sampling and then go again. Right. And then you can do that again, but this time on the offsets be across the Y and not the X. And the final one is the offset across the X and the Y. So that will get, this will sample a 4x4 set of pixels, so 16 pixels all in all. Very nice. So after we've got all that block filled in, we simply just say return block. Now we're not quite finished here, there are still going to be some compile errors on this block. So that'll be block.texels basically. And that should be everything. I think I've renamed texture there actually, that's good. And voila. So that's one function down. I might want to change the name in a bit. Maybe I can call it BC load texels RGB, something like that. Much better. Cool. So this next one is load texels RGB bias. So you see, I wonder, this is where it's like a MIP bias. I want to see like, so there's this sort of like MIP 0. It just does a load texels, then a BC1 block compression, right? Why don't we just port that first? I think porting all of the code might not be, we'll see, right? Let's see what this is doing. This is block compress 2 MIPs. So it seems like it does MIP 1 and MIP 2, maybe? Let's see. Right, catch you later, Dyson Slice. Good to see you. Yeah, have a good one. So this one does a downsample MIP. Loads of texels from in our MIP1 block. Right, so it just loads the same texels that it loaded here. and then just block compress them. So those are the texels. And it downsamples it, right? It's not really downsampling though. Average out the colors later by passing the scale value into BC1 block. This allows us to avoid scaling all 16 colors in the block. We only need to scale the min and max values. Right. So it takes a min max and then it, right. Okay. Right, so since adding and then dividing it will produce the same. If you use to min and max the sum of everything and then the average or the mean average of everything, the min and max value will still be the same. Yeah, no matter which way around you did it. Right. Yes, this is more of a performance optimization, but it means I can port less code. I've got a fast downsampler which does it a mean, or it can do a mean downsample. It's what I do anyway. And plus I'll be doing more than just color data anyway. I think this will be fine. So block compress. Right, so that's just for MIP1. What's this? So for MIPS, for the rest of the MIPS, what is it doing? It's loading the texels with a MIP bias, and then it's compressing the block, and then outputting it to a different texture, basically. Yeah, we don't need all these different shaders. So this is great. This heavily simplifies the code. So this MIP bias one, we don't actually need this, right? Goodbye. Load texels RGBA. Now, RGBA, that is needed for BC3, because it's got a BC4 block, hasn't it? Yeah, so we'll need this one. But again, that's not too bad. Yeah, it says different A. Nice. This is cool. So we'll call this a BC. Why don't we just call this a BC1 block? Block texels. You could just call that block, to be honest. Yep. And then we'll have another structure for a BC. Now it's saying there's a BC3 block, but that just has a BC4 part to it, I think. Pretty sure. So I think we should have a BC4 block, basically. And that just has the texels in there. And then a BC, I'm pretty sure BC4 is a... Let's have a look at this. Alright, so BC3 stores RGBA data using BC1 for the RGB and BC4 for the alpha part. Yeah. So we'll be able to... Like, they haven't got a BC4 compressor in here, but it's in that BC3 block compressed code. So we'll be able to do that. So maybe we can have a load. So the alpha channel, basically. And then if we have a BC3, we maybe that would be a BC. Just one of this, right? So it'd be a. Yeah, I want. What does BC5 use then? Yeah, loads 2. Load Texel's UV, U and V. Yeah, so they're just doing 2. Yeah, it's BC5, isn't it? Yeah, so I have a BC4 block. So it'd be a BC1 block and then a BC4 part to it. And that'll just be returned from a function. And then we'll have a BC5, which is 2 BC4s. So we'll have that sort of RNG, basically. Yeah. So BC1 load texels, or maybe BC1 load block. So there's a 4x4 block of BC1s. And then this is the load BC3. So it's the RGBA, right? It loads the BC3 part and BC4 part. Now, my concern is though, oh yeah, we can do that easily. Right, this doesn't do a smart gather. Why doesn't it do the gather? You've got gather alpha though, that's the thing. Like, we could totally do code like this. Right, let's take a quick break. Be right back. Welcome back. So it seems like, you know, this code up here can just be repurposed for this code just down here. Like, it doesn't seem too crazy. Because this could be, you could do gather red, and then it should technically be quicker. This is just doing a bunch of loads. And yeah, so let's just make the code work for RGBA. So we'll keep the other code just for a second while we make this. Let's just put ours here at the bottom. So yeah, this would be the block, the BC3 block. Got our sample, got the text source, we did this sort of local. We'll take the inverse texture width as well. Right, so dispatch local index. So this is the old code list. F0 for people who are just coming in and looking at it. So essentially, it's the same thing, but we need to add a gather alpha, which is the thing. Maybe this wasn't a thing some time back. I don't know why they haven't done it this way, but you can do it. Right, so we have this gather alpha. Let's repeat it to all the other 2x2s. All you have to do, so there's block, there's a BC1 part and there's a BC4 part, and that's where the alpha goes. So BC1 dot texels, BC1 dot texels, BC1 dot texels. Okay, so now the final part is the 4 alphas. So you just repeat that, and it'll be BC4 alpha. Now it was probably in the same way, so it's .w z x y. So if we take these and duplicate them for here, but all we have to do is make sure that we copy these 4 indices and repeat them. Well, that's working out well. So that is 8, 9, 12, 13. All right, so that is basically it. So that's the BC3 load. Voila. Cool. And the other one is the BC. This is with a bias. We don't care about the bias because we already have a downsampler. I think we'll just use that and just block compress every downsampled image manually. That's what seems like is in it that way anyway. With a tiny bit of a speed up by avoiding doing some extra divisions or something like this. So I'll just have a simpler code base. So load texels UV. This is the code for, yeah, this is the code for the BC5. So I'm wondering if we can just take the BC UV. Is it the same numbers? 0, 1, 4, 5, 2, 3, 6, 7. Yeah, then the 8, 9, 12, 13, yep. Yeah, it is, right. So basically, all we've got to do is take this one again, right? And, you know, it might be worth actually taking this one, the BC3. Getting rid of the blue in the alpha channel. You know, I should have just copied the whole damn function. crap happened there? Cool. So yeah, we'll just copy paste it, basically rename it to BC5. That's got two BC4 blocks, right? BC4 is just a grayscale. So it's two grayscale images. Now the sample texture could actually be different, thinking about it. This one's going to probably just be like this. A vector 2. To be a BC5 block. And we are just going to want to do a blue and a red and a green, so we get rid of the blue and the alpha channels. And then now it's got to do some magic here. So we've got a BC, so we've got an R section, which is where we just have red. And then we have a green section. Like that. So it's got to repeat that for the rest of them. So R, G, green, red like that. Amazing. R, G, green, and then red. One more. Okay, so that's looking pretty good. So that's 4 different functions to load the uncompressed textual data into some structures, ready to go basically. Now, so we don't need this function. This is the one we just recreated above. Don't need the bias one because we're not really using bias. Now this is where got some utility functions. So there's get minimax channel. You can probably do this with wave intrinsics. Because if you're doing a 4x4 block, right? Like, I don't know why I'm just not running a specialized shader for this. Why do I need these special functions, you know? Like, I should have a shader called BC5 compress. You know, I might need to... Yeah. The thing is, yeah, you can just use like wave intrinsics, and yeah, I was thinking we might want to have these BC compressors for other reasons. But yeah, if you had we might make 2 of these functions, one for wave intrinsics, one for without, because that will allow you to, yeah, it'll just be a lot quicker. Alright, so let's take a look at the block compress functions themselves. So BC1 block compress is a get min max RGBA, as you would expect. Then an inset min max based on a color scale. So by default is 1. Interesting. What does this do? Right, slightly insert the minimax color values to reduce the RMS error. The Richard Stallman error. This is recommended by this guy. By Van Waveren and Castano. Very interesting. So yes, just slightly shrinking the... Yeah, slightly offsetting the min and the max. So they're not so far wide apart, basically. Right, so after that, is that all it's doing? Then convert to 16-bit 565 color. And then compute these indices. For the alpha channel, I thought we didn't want an alpha channel. Right, so the alpha channel is encoded into... Ah. I thought it was encoded into less bits than that. It's got 32 bits for alpha. So that's 2 bits per... Ah, yeah, that's 2 bits. Wow. It compresses 16 pixel color information into 4 bytes. It's pretty insane. And then there's another 4 bytes for alpha. Right. It's a lot smaller than I expected. So there's 2 bits for each pixel for alpha, by the looks of it. Is that right? Right, let's read this. Store 3 component color data using a 565 color. This is true even if the data contains 1 bit alpha, assuming a 4x4 texture using the largest possible. Right. PC1 reduces the memory required. It's heavy compression. Interesting. Like, oh, okay, I'll look at that one. Thank you. Yeah, that'll be good. Yeah, it says indices, which is interesting. I don't know what that means. Well, I know what indice is, right? But yeah. PC1 reduces the memory required from 48 bytes to 8 bytes of memory. The algorithm of 4x4 blocks of texels instead of storing 16 colors, the algorithm saves 2 reference colors, 0 and 1, and 16 2-bit color indices. Blocks A to P, as shown in the following diagram. So there's 2 byte. Yeah, these are both 2 bytes, and these are all... Yeah, I guess 1 byte. Right, okay, so the color indices A to P. Alright. I used to look up original colors from a color table. The color table contains 4 colors. What color table is this? Interesting. The first 2 colors are 0 and 1, which are the min and maximum colors. The other 2 colors are color 2 and 3, which are intermediate colors calculated on linear interpolation. Interesting, right? Ah, right. That's right. Ah. So there is no alpha. I can't see the alpha then. Maybe the alpha is explained later on. Right. Okay, that's really interesting. So it's able to. So there's technically up to 4 colors each pixel gets to pick from. Eh. Don't know what the crap happened there. The 4 colors are assigned 2-bit index values saved in blocks A to P. Right, good. Finally, each color in blocks A to P are compared with the 4 colors in the color table at the index closest. And the index for the closest color is stored in the 2-bit blocks. This algorithm leads itself to data that contains 1-bit alpha also. The only difference is that color 3 is set to 0, which represents transparent color. Color 2 is a linear blend of 0 to 1. Yeah, but how do you set it to... I thought color 3 was implicit. Right, but that's only if you use the RGBA variant of BC1, maybe. I'm confused now. BC1 yeah, there's a BC1 RGBA, so that will set color 3 to be 0. I see. Wait. Which represents a transparent color. So it's kind of 1-bit alpha, I guess. It's a bit weird. That's interesting. So BC1 stores 2 colors, ESC1, C0, they define the RGB space. Define a line in RGB space, yep. C2 and 3 then lie on this line, yep. If C0 and C1, or C0 is less than C1, then C2 and C3 lie on this line. If C1 is greater than C0 is greater than C1, then C2 lies on half to this line. Oh, interesting. Right. So you... Right. I see, so you put it the other way around, right. I see, yeah. Oh, they've got it here. If min color is less than max color, get indices. If not, the indices will be 0. No. Yeah, let's look at that Wikipedia page. See it under texture compression. S3. Right, thank you very much. Is it DXT1? Right. If C1 is greater than C0, these colors are interpreted using the 6. Compare these colors by interposing them as 216-bit unsigned numbers. Then the two colors are calculated such that each component. This mode is similarly to the mode of 0C0 of the Apple the codec. Otherwise, if color 0 is less than 1 and C3 is a transparent, is transparent black. What's corresponding to pre-multiplied alpha format. Yeah, so this is explaining it slightly differently. Right. But where does C3 come from? That's the strangest thing to me. So if C0 is greater than C1. So what's interesting in this code here is it's saying if the min color is less than the max color. Now that is basically saying if the red channel or whatever is, then get the indices. Something like that. What does it pack in the high bits? Let's have a look. It's up here, wasn't it? Yeah, the red channel. Packs that in the high bits. It's not saying if all of them are less than, it's saying it's kind of weighted towards the red, then green, then blue channel. So yeah, then get the indices. Huh. Right, so compare these colors by interpreting them as two 16-bit unsigned numbers. Ah, okay, so this is exactly what this is doing here. Then two colors are calculated. So yeah, so the indices are not needed apparently for this. Such that for each component, C2 so the third color C2 is equal to 2/3 of C0 and 1/3 of C1. And C3 is this. This mode is similar. Okay, so it's just some special mode. Just another special mode. And if C0 is less than C1, then C2 is equal to this basically, and C3 is transparent black. So it just is set to transparent black. Right. I see what's going on. So it's got a sort of a 1-bit transparency mode somehow. Right, I see what's going on. Bit weird, but I didn't realize how low it compressed it. So I'm sure we're going to see lots of visual artifacts of this, but we'll see how it looks. It's useful to have around as well. So you've taken a color block, there's a color scale. So what's this color scale thing? It's stored in linear address space in data compression. So you get 1 bit of choice information just in the ordering. Yeah. Yeah, that's it. Yeah, it's interesting. I'm not quite sure exactly why that is, but yeah. Color scale is a scale that is applied to the input colors. This is an optimization when compressing 2 MIPS at the same time. When compressing a single MIP, color scale is always 0. Right. So we'll get rid of that then. Okay. Right. Yeah, so I reckon you can wave intrinsic these. We'll wave intrinsic this one, it's quite easy. Right. Yeah, you can't wave intrinsic that one. It's a bit too fiddly. Okay. So let's get min-max color RGB. It's going over all of... Yeah. I guess we could offer a wave intrinsics version. It's not too bad, you just need an if statement. So just the low half and then the high half of the wave 32, but let's not bother doing that just yet. So block.texels. Alright, so we've got to return this sort of min-max. So I guess we need another structure called BC1 min-max. because I don't have out variables yet. Where else was this used? It was using color 3. Set min max. Yeah, it's just doing the same thing. It's right, it's BC3 block compress. So yeah, it's doing the exact same thing, obviously. And then you want the indices as well, the BC1 indices. So min A, B. Pack our colors and alpha into units. Right. I see. Yeah, so I think we won't make a separate function for this. So we'll calculate the min and max color. This will just be directly inside this one here. So this block compressor will just return a U32 times 2, and we can reuse that function for BC3. Because BC3 has a BC1 block in it, basically, right? So BC... Yeah, this will work. Right, max color. Cool, cool, cool. So we instantiate those to this, basically. And then we do this for loop. So we could do a wave intrinsics version, maybe. Might be better. Yeah, we'll write this out first. So there's this inset min max. Now that gets passed into the color scale was 1, wasn't it? We don't need that anymore. So we could remove this. Right. Okay, so I guess we'll put that comment here. Still kind of useful. So this color scale can now go. We don't need the color scale. So that is a vector 3. Now the bottom one was an add, so not going to forget that. Okay. Right, so this needs to do a... Yeah, so it's kind of doing a divide, but okay. So it's doing a multiply by a scalar. Boom. After applying the offset, we want to round up or down to the next integral color between. Ah, shoot. So you need color scale to be there then. Yeah, you do. So it was multiply. Two five 5.5. That was the way it worked before, I think. Yep. Cool. Yeah, good. Right. That's looking all right to me. So the next one is pack our colors into events. Right, good. So this would be the min-max color packed, basically. So that would be pack 565, I think I called it. So no color scale thing anymore. Got rid of that. Sweet. So then there's this thing called indices. To reduce error. Right, so indices. Right, so where is this being used? BC block 3 only, right? That's right. Yeah, good. So we could just inline all of this basically. All right. So min-max color and block goes in. Yeah. Gotcha. All right, let's port this code over. So for each color, for each input color, we need to select between one of the following colors. Right, we'll keep this comment in. Min color packed. max color packed. Cool. So this sort of subtraction here. Max color. And then min color. All right. Good. So that would just be, right, I'm just changing that one. Cool. Right, so step increment, I guess that means. So scale up by 3 because our indices are 0 to 3. Okay. Nice. So dot product. And then another dot. Scalar, so it's all good. Yep. Right, so 15. Yeah, that'll work. Right, so compute the index for this block element. Right, so truncate, add 0.5, let's stick with that. Nice. Right, sort out the indentation here a bit. Cool, so the other thing as well, we don't really have uint, so let's sort that one out. Okay. Nearly there for this function. So this block needs to be block.texels. That's what we've changed it to. Yeah, right, that's looking good. So that calculates those 2-bit indices for the 16 pixels to say which one of the 4 colors it is. And then it will pack that down into a U32 times 2. So that'll be a min color packed, shift left 16, then max color packed. Okay, so that is this function which block compresses a BC1 block and returns this. Now, this can be done to do, you know, maybe we could offer a BC, you know, we could do a wave 32 version, maybe. Why don't we just do that now? It's not too hard. So we'll have this sort of underscore version from the minimax. And we'll optimize this code here basically. So we'll have a block compress standard one, which just does this and calls the underscore version and returns that. Yep. Then we have the wave 32 version, which will be an optimized version of this. So the way we can do it is we'll need a local index, I think. No, we won't. So get the wave in, you will get your thread index. So we need all active lanes basically. So we'll say wave active sum 1. So each thread within the 32 waves which run in lockstep will have a prefix sum. Yeah. So each thread will get a 0 to 31 basically, depending on which thread it is. That's what I want, isn't it? Yeah. So then this will allow us to say if thread index is less than 16, and you have min-max color, and you just say min color equal wave active min, so all the active threads, so all the threads from the first 16 threads will run this code and then output min color into there, so that'll be block texels thread index, right? And then you have wave active max. And then you basically have an else with the same code. In this case, just happens to work out that way. And voila, that avoids the for loop. So the first 16 threads go here, the next 16 threads go there, and do the same thing. And this means they all get, the first 16 threads will have these values, and the next 16 will have these ones. These won't go into an SGPR because we'll have different values across the whole 32 threads, unfortunately. But there we go. Yeah, I wonder if there's anything we can do. So you'll be doing 2 blocks in a single wave, is that right? You will when you 2 4x4s, there'll be an 8x4. Yeah. It's interesting. Cool. Wait a minute, that means you won't be able to... Morton code. No, you can Morton swizzle it, I think. Yeah, the Morton swizzle will work. Yeah, it would need to be Morton swizzled. Okay, good. So we'll say, so first 16, that will get you a 4x4 block. Yeah, so that must be... So, must have no inactive lanes and be Morton swizzled. So we got that sort of swizzle, yeah, like an 8x8, something like that. Right, must have no inactive lanes in a block. Easy. Cool, so that's the optimized version. So basically BC3 will do the same thing. Well, no, we'll use BC. We need a BC4 one now. So where's BC4? So BC4 is this. Round. There's a value scale as well. We'll get rid of that. So we just produce a min-max alpha. There's no special table. It's quite easy. So we just want to be able to block compress BC4 now. So, right, let's delete this code. Oh no, not that code. It's one I want to keep. Want to delete this code here. Get indices alpha. Ah, they do it for the alpha. Interesting. Oh, we'll need to keep that one. We'll need to read. Right, interesting. That's the BC4 RGB. Min-max RGB, we've already done these. Give it min-max UV, it's just doing a min-max. Oh, we'll need that. Min-max channel. Yeah, this is BC4 min-max. Obviously, it's quite obvious, isn't it? It's just a for loop. Cool. So we'll need to port this over. It's not too hard to port that one over. Right. So let's create a BC4 compress. And it's probably... Yeah, let's create that. We'll probably want to pass in a min-max as well, but we'll see. So this will return a uint. So U32 times 2, BC4 compressed. So this does a single alpha channel into 64. Sorry, it does 4x4 pixels of alpha. So single channel compressed into 64 bits. And the value is meant to be from 0 to 1. So BC4 block goes in. We might have a min max value. Min value, max value. That'll probably come in. We'll calculate those like we've done with ones above. So looking at how it works, it seems like the BC4 gets its min max here with a min max channel, right? Then there's no inset thing happening, but it does the get indices. So we just need to pull that get indices thing. So it's basically all of this whole function here. It shouldn't be too bad to port. It's just floating point at the end of the day. I want to get rid of those tabs though. And that horrible camel case. Right, so min A, min max A. Right. Okay, so we'll get rid of that. Right, so the step used to be 3, but you got 7 different values here. Right, that makes sense this time. Step ink, right. Cool. Alright, what else we got? So we got this like for loop going on here. We don't have units in the code base. Get rid of that. Right, for each alpha, let's look at that one. Right. Cool, so this is around... Well, the way we are doing it is probably... Nice. Do we have another round on that other one? No, there wasn't an inner loop. Okay. Alright, that all seems pretty legit. What's that for loop doing? I messed something up here. What's that? Huh. How did their code even work? You're an I that's declared here without... Yeah, that must be a compile error. They've already got that in their code. Yeah, that should be a compile error. I don't know what's going on there. Right, just fix that up. Nearly messed that one right up. Not really. Okay. Good, good, good. Right, so that will return... That gets the indices. I might want to put that into a... Right, so that would... Packed, it was called. So, packed. So this is or equals, so they must be initialized to 0. Why did I say uint2? I meant to say a u32 times 2. It's not HLSL. Right, so that gets the indices. So it's like get indices alpha. Out A. So it's initialized to something here. Oh. You're telling me it modifies A as well? A dot. It modifies the minimax alpha values which are packed in there. For each alpha value, we need to select one of the 8 alpha values. Right, some interpolation between those. Now we need to convert our index into this scheme or whatever, and then it's ORing. Why is it ORing into pack.x? Seems incredibly wrong. We should look at BC4 in the... Where's BC4 like? Well, I can see in the code really, it stores... Yeah, it just stores them as a 0 to 255, right? It makes sense. The min and max value. And then... But why... It makes sense why the Y column is changed, because that's where the indices go. But I'm interested in what this loop is doing. Then it's storing the index. So index 0. You've got 8-bit, not 8 bits. Oh. Of course, it only needs to store 1 byte. Right, I see it now. It's a U32 times 2. It only needs 16 bits. Yeah, 16 bits to pack in two 8-bit values. Then the rest of these indices, 3-bit indices, sorry, 2-bit indices are stored. Some are still stored in this word, right? Makes a ton of sense. I see now. Right. Okay. Makes a lot of sense. And the shift starts at 16. Yeah. Got it. Cool. So we can delete this now because we've ported into our other one. Right. So we've done our BC1. So that gets the indices. We need to do the there's the packing. Didn't name that properly. Good. Right, so these are the packed versions. They didn't really use the packed versions, did they, in the... Right, so it's max v packed. So I guess this overall would be, we should just call it packed actually. Right, so afterwards we, yes, you need to do the packing. So that'll be, I think it's min v packed shift left 8 ORed with max v packed. But then we will need to shift it left by 16, is that? No, we won't. Yeah, that's right. Good. Now, only if this is true do we do this code here. Because the way the format works, it's got a special mode where if min, wait, if max is less than min. It's got a special mode for that, where it doesn't need the indices. Okay. There's no scale needed. Right, that's all looking good, and then that should just return packed. So that's the BC4 compress. We just need a min and max. I think that's right. BC4. Yep. So we just need to do the special, like we've done for BC1. We've got one which just does a for loop and another one which does the sort of wave 32 version. I can't do the wave 32 of these, doesn't work. Or it's too complicated. So BC4, BC4 block, BC4 block. So we'll have a min value basically. And we'll just go over all of them and do a min. Right, it's quite basic. So block texels. Then we'll call BC4 compress min max value. So here we're doing the same thing, but a bit more optimized, hopefully. So it's using wave intrinsics with the first 16 go here, the next 16 go here, and they do it all in a single instruction. So yeah, it's doing 2 blocks at a time. No, 1 block at a time, basically. In single instructions. So that'll be something like that. With BC4. Rightio. Very good. Cool, so that's BC4 there. Now to do a BC3 compress and BC5, it's just combinations of BC1 and BC4. Not confusing at all. So yeah, we can just get rid of all this now. Actually, no, we can't. We've got to keep this. That's the BC4 block, right? Or the BC3 the way it compresses. So, right, so with BC3, it's a BC4 and a BC1 block. So, the way we'll do it is we'll call... So we'll get a BC1 by doing BC1 compress block.bc1. Then we'll do a BC4 compress like that. And then we just take that last line and just do this basically. So that'll be, so out.a is the packed BC4. So it's BC4 x BC4y. And then here's BC1.x, BC1.y. I think that's right. Let's just double check it. So the BCY, sorry, the BC1 is this min color, max color, this here, and the indices. Yep. And there it is, it goes into there. So that's as we expected, right? So our BC1 also does that. I've just inlined all the code. Yeah, there we go. Good. Cool. Right, we're nearly there then. So that's the BC block compress. Now we're going to offer a wave 32 variant, which will basically do those, you know, min maxes and stuff using wave intrinsics. Cool. So there's a final one, which is BC5, and that's two BC4 blocks stuck together. So we should be able to do a BC4 so yeah, BC5, it's got two BC4s in there, so I've called them R and G, and that'll just be BC4, so yeah, we'll get back an R and a G. Now it must be obviously some configuration of this, so we'll look into how that is. So BC5 is, yeah, U and, okay, as you would expect. Alright, pretty easy. So all we have to do now is do a BC, there we go. The first BC4 goes there, as you would expect, and the next one goes there. Cool. So the wave intrinsics one, we'll just do wave 32. Voila. So I think that's all the code ported over. We just got to get it compiling, and then we've just got to write special shaders, which will just basically do the load and then do the store, and that's it. So it's pretty close now. So I might change the, so that's block compress. I might change these names. Where are they? Oh, we don't need any of this anymore. So I called it load block. We'll call it block load to keep it consistent. That loads in the block of text source over sort of pack 565. Pretty legit. So let's go ahead and see if it still compiles. Right, plenty of those are completely missed. Yeah. Cool. Texture. Right. So that's because I did a gather. Yeah, I forgot to change this. So that would be a float 32 times 2. Yeah, that was on the BC5. Oh, have I not got BC4? Oh, we missed the BC4 load. That's not too bad though. We'll just do a gather red. So we'll copy because the Microsoft one only had BC 1, 3, and 5, but obviously BC 4 is part of BC 3 and 5. So I've just made it into its own thing. So I just missed that for this one. So that's just a single floating point. BC4. Just need a red channel. And then we need to get rid of all those R's. Yep. Then there's one other thing. Yeah, this needs to be a crap. This is meant to be a yeah. Gather red, float. Is that BC5? That is meant to be a 4. Yeah. Shoot, my gathers wrong. I need to regenerate the code gen. So my gather functions are wrong. I remember fixing that in the past, where the gather was... Because open the gather, it gathers 4 pixels, and it needs to return... Yeah, okay, I need to regenerate that, damn it. So that is in... Let's go into the compiler quick. So there's a generator for that, there's a... scripts intrinsics gen. Oh crap. Texture intrinsics, texture gen. Right, so in here there's a special one for sampler. Or gather, right, isn't there? Yeah, gather, can gather. Right, so the gather functions, gather 4 texels, VI. So we should probably call it vector G. I don't know if I've done a VG yet. No, we ain't. Okay, it's good. So we'll look for I. And VG. So what we're trying to do is we'd need to get the scalar type of the right, so there's a data type. Yeah, data type suffixes, we want that. And then we want to basically put a Oh, no. Yeah. And then you want to put the vector 4 suffix on it. That'll do it. So that's for the gather. So when we run that, that should generate us a better. So we go scripts intrinsics gen, and then do a git diff. There we go. So you'll see that the return type has now put the scalar suffix and then the vector suffix on those gathers there. And that should automatically work without any compiler changes. We just bring that over and it should just work. So that'll be, let's just get over into there. So HTC, texture intrinsics, game. Third party, HTC, plop that in there. All right, so we run that. Damn it. What happened here? Gather green. Oh, I didn't change it for the green. I didn't change it for gather red, didn't I? Of course. Hang on a minute. Gather. Right. G for green, or G for gather on the gather green, blue, and alpha. Regen. Yoink. Cool. So we got past those compile errors now. The next one is a 1669. Right, so we've got some right, I need to divide by scalar. That's one. Cool, there's a uint in here, so 73. Couple of quite a few uints there. $88. So that is a moles diag right. So we didn't do a block.texels at some point. That's at 1778. Right, block.texels. Right, this is a uint 4, we don't have those. Slightly different name. Right, and that return type is wrong. Yep. Right, there's a Wave 32 version. And voila, there we go. So hopefully it doesn't crash the compiler, but that should, there we go, good. So, all that's left to do now, so we've got the block compressed code all ported and compiling. And that does BC 1, 3, 4, and 5. So it should do everything we need. So now all we have to do is write a shader, which will take our textures and call those functions that we ported over to read the blocks in, compress them, and write them back out into the block compressed texture. So yeah, Yeah, so I reckon we'll be able to get that done next stream. That should be quite easy to do. Then we'll have stuff block compressed, and we should be able to have a way to toggle it off and on, just to see like if there's any visual artifacts there. So that'll be on Thursday's stream, which will probably be about 3 hours ago from now, but on Thursday. And then there'll be another stream about 4 hours ago ish, but on Sunday. Right. So in the meantime, guys, there is a Discord channel. If you want to chat in the meantime. And what else? Yeah, I think that might be it for now. But yeah, I wonder if we should try and fix the normals and see if we can block compress those after we've done this. Because I think my normals are not being generated the best. We've got a... Hey, Cranston. Yeah, I'm interested. Yeah, definitely. Hopefully it works first time. Hopefully, but probably won't. There'll probably be one thing the wrong way around. Not that one. It wasn't this one, wasn't it? Yeah. So my normals here are kind of all pointing the same way for these ones. They're very much pointing the same way. So this texture kind of looks really bad when I generate it from a height map. So I've got to improve my code. If I put this if I block compress this texture down, it's going to look horrible. This is using 1616 unorm. If I use 88 unorm, it's terrible already. So I've got to try and see if I can improve my normal map generation, and that might mean we can block compress some normals, and this could just look alright. It would be great if we can block compress those normals. I'll be happy if we could do that. Well, I'll be happy anyway, but yeah, I'll be even more happy. Right. Yeah, it just depends on how close we're going to be to the thing, but, you know, to the surface, you know, I don't know. It is in tangent space. I would expect it to be, you know, easier. But, no. Well, it already is compressed, right? We're already dropping the Z component and reconstructing it. Trade the Z guy. I was seeing if there was any more sea folk, but no sea folk. Alright. Have a good Wednesday, guys. Hopefully we'll see you all Thursday. If not, Sunday. Catch you all later. Bye.